quite often in the real world we're dealing with functions that we don't know very much about. We don't fully know what all the independent variables are and how they affect the outcomes. And in that case, we usually collect a lot of data and make a model. And this involves quite often fitting a function to the model and finding the best fit. For example, you might look at your data and try to fit a polynomial to the data if there's one independent variable and one dependent variable, and search for the best polynomial function which fits the data. And after you form your model, then you need to test it on data that hasn't been used in forming the model. So you make your conclusions and then you see how good this is at predicting events in the future or on a different set of data. And of course, if it turns up that this model is not good at predicting, then you go back to square one and you think it all through again. So this model is an idealized representation of reality. It mightn't be a perfect fit, but a good model doesn't really have to be a perfect fit. It should simplify reality enough to permit mathematical calculations, but it should also be good at prediction. So now what we're going to do is look at the graphs of several functions that are quite often used in modeling reality. Now the simplest model that one might use is a straight line. Here we have some data on levels of CO2 in the atmosphere over several decades. In 1980, there were 339 parts per million of CO2 in the atmosphere. And we can plot this point with two axes. On the horizontal axis we have time, and on the vertical axis we have CO2 levels. So this point here, we can plot it on the TCO2 plane. It goes above 1980 and straight across from 339. And again, we can plot all of the other points. And what we're searching for is a line that fits the data. And you can see here, if we draw the unique straight line between the first and the last data points, it fits the data reasonably well. So we might use that as our model to predict future levels of CO2 in the atmosphere. Now, of course, there are several options for choosing a line that fits the data. In statistics, you usually use the least squares line, where the sum of the square distances from your points to the line are at a minimum. And that's something you'll learn about in statistics. Let's go with our chosen line here. What we need to do is find an equation for this line. And remember, the equation looks like y equals mx plus c, where m is the slope of the line. So we can find the slope of the line here by taking these 2 points on the line and using the formula for the slope to figure out the slope. So the slope is the difference in the y values over the difference in the x values. And that turns out to be 75 over 40, which is 1.875. And now, using the point slope form of the equation, we get the equation of the line is given by y minus y1 equals mx minus x1, or y equals mx minus x1 plus y1. And when you fill in the details, this is what you get. Then, to predict the levels of CO2 in the atmosphere in 2030, we use the point on this line for prediction. So our prediction would be the y value associated with 2030 on this line. How do we find that? Well, the y value we get when we plug 2030 into the equation of the line is given by 1.875 times 2030 minus 1980 plus 339. And of course, that turns out to be 432.75. And you can check in future decades how well this model works and whether you want to revise it by perhaps fitting a quadratic or some other polynomial to the points.